Welcome to section 12.4. In this section, we're going to be looking at the other type of kind of quote-unquote vector multiplication. We looked at the dot product in the previous section. Here we're going to be looking at the cross product. So if we have two three-dimensional vectors, A and B, the cross product of A and B is going to be denoted with this symbol, looks like times, but in the context of vectors, this is a cross product, and it's going to create a new vector. And the formula for that vector, we're going to put the formula down now, but then we're going to look at a way to kind of develop a process for the cross product rather than just blind memorization of a formula. But first, here's the formula. So we're going to have the first component is A2B3 minus A3B2. Second component is A3B1 minus A1B3. Third component is A1B2 minus A2B1. So that's our formula for the cross product. Now, the better way, the more effective way, and more kind of topical way to what we're going to be studying, we're going to develop that here in just a moment. So the first thing we need to look at is the concept of what we call a determinant. So if we want to find a determinant, this is going to produce some value using a grid of values, either numbers or vectors or variables, whatever the case may be. We have this little 2x2 matrix here, this little grid here. If we want to take a determinant of order 2, so that's of a 2x2, basically we take AD minus BC. So we go across the diagonals there. So that's going to be AD minus BC. All right, so this is a formula we have for these little 2x2s. So for example, if we had a determinant and we had 2, 1, negative 6, 4, and we wanted to compute the determinant of that, so we would go 2 times 4 minus 1 times negative 6. That's a negative with a negative is positive, so that's 8 plus 6, which is 14. So we get that the determinant of this little 2x2 is 14. The determinant of order 3, so if we have a 3x3 grid here, so we've got A1, A2, A3, the B's and the C's. The way that we compute this determinant is a little bit trickier. So we're going to take the first row and we're going to use those components. So we're going to start with A1. And then what we're going to do is we're going to block off the row and the column for the value that we just used. So for A1. And now what you have left here is a little 2x2 determinant of the values remaining. So it's going to be A1 times this 2x2 determinant. And that's the first one. Then we move on to A2. We block off its row and its column. Now, there's a little catch here. It's not going to be plus A2. It's actually going to be minus A2. Okay, so it goes plus, minus, plus. It kind of goes back and forth. It alternates like that. There is a reason for that mathematically, but it goes a little beyond what we're going to be studying here. So we get A2, we block off its row and its column, and we're left with this 2x2 right here. So that's B1, B3, C1, C3, and then plus, so again, plus, minus, plus. We do A3, block off its row and its column, and we're left with the little 2x2, B1, B2, C1, C2. And then, of course, we could compute the 2 by 2 determinants using the method that we just saw back up here with that formula AD minus BC. So for example, if we have a 3 by 3, so we've got 1, 2, negative 1, 3, 0, 1, negative 5, 4, 2, just as an example. So we go first component up here. So let me do that. So that's 1. We block off its row and its column, so we're left with that 2 by 2 down here. So that's 0, 1, 4, 2. Minus, move on to the next one. So that's 2. Block off row and column. That leaves us with those 4. So that's 3, 1, negative 5, 2. Plus negative 1 times, if we block off row and column, we're left with that 2 by 2 right there. So that's 3, 0, negative 5, 4. And then we can compute the 2 by 2s. So that's going to be AD minus BC. So that's 0 minus 4 minus 2 times, that's 6 minus negative 5. So that's going to be plus 5. And then this is minus 1 times, that's 12 minus 0. So let's see what we get here. That's a negative 4. This is an 11 times 2, so minus 22. So that's negative 26. Minus 12 is negative 38. Is the value we get for that determinant. Now, what does this have to do with the cross product? Well, if we go ahead and take a look at our cross product formula again, but this time we're going to use the standard basis vectors, that IJK notation that we saw a couple sections ago. So if we consider our two vectors A and B here, then A cross B, using our formula, that's A2B3 minus A3B2 I plus A3B1 minus A1B3 J plus A1B2 minus A2B1 K. And you might notice there it does bear some maybe potential similarity to some of the stuff we've been doing back up here, kind of the general form of some of these. Now I want to rearrange this a little bit, just the middle one. So if we go ahead and I'll just make this change right here. I want to pull a negative out of both of these and make this negative. So if I make that negative, basically I pulled the negative out of here, so this one becomes positive. This one was positive, so now it's going to become negative. Okay, so hopefully that makes sense. So, right, this is going to be minus, that's going to be minus, that's going to be plus. And then one more little algebraic switcheroo here. I want the positive one in front, so I'm just going to switch their order. Okay, so the new version that we're going to get is minus A1B3 minus A3B1 J. So hopefully everybody sees that. I pulled the negative out here from both, and then I switched their order so that the positive one would come first. Okay, so then I'm gonna just slide this right in there. Now, each of these individual differences, so this one, and this one, notice they do bear a striking resemblance to that AD minus BC formula we saw from the 2x2s back up here. So what we can do is we can kind of work backwards. Instead of going from the 2x2 to the formula, we're going to use these formulas to create 2x2s. So this first one, instead of AD minus BC, so we're going to get, this is A2, B3's down there, A3, and B2 down there, and the I is still there. Minus, we do the same thing here. That's going to be A1, A3, B1, B3, J, plus A1, A2, B1, B2, K. Now, if we compare this to what we did with the 3x3s up here, this pretty much mirrors that formula, and this is why I wanted that minus in here, so that we could match the kind of back and forth that we get with the 3x3 determinants. So now let's go ahead and undo this step from here and go back to a 3x3 and see what that looks like. So this gives us, this will end up being, instead of A1, A2, and A3, we have I, J, and K. So those are going to form our first row. So we're going to have I, J, and K for our first row. Now, technically, those aren't numbers. Those are considered to be vectors, but think of it as we're using them as like a placeholder. They're just kind of filling in for the values here because we know in the end we're going to break them back out and turn them into a vector again. And then from here we end up getting A1, A2, A3, and B1, B2, B3. So this is A cross B. And this is the formula that we're going to be using to compute the cross product of two vectors. So instead of having to memorize that formula, we are going to just create a 3x3 determinant here with ijk in the first row always, and then the first vector and then the second vector. We just put both the vectors into the rows and compute the determinant. So we compute the 3x3, right, by breaking it into the 2x2s, and then compute the 2x2s using just AD minus BC. All right, and this process, it will get a lot easier the more that you practice it, but it also does lend itself well to future topics of study in this class and in upcoming courses as well. So this is a good technique to learn right now. So let's take a look at an example. Let's just try one out. So we've got two vectors. We've got A and B here. So if we go ahead and cross A and B, we're going to get, so I, J, and K with 1, 3, 4, and 2, 7, negative 5. All right, so we're going to go the I component first, which means, right, we block off row and column, so we're left with this 2x2 here. So that's going to be 3, 4, 7, negative 5, I. And remember, it always alternates plus, minus, plus, so it's minus, block off row and column for J. That leaves us with those 4. So that's 1, 4, 2, negative 5, J. Plus, we get, for K, we block off row and column. That leaves us with this 2x2. So that's going to be 1, 3, 2, 7, K. So again, plus, minus, plus. The J is always getting that negative tossed in front of it. From here, we just need to compute the 2x2s. So that's going to be negative 15 minus 28 I minus -5 minus 8j plus 7 minus 6k. Now you have to be very careful not to get this mixed up with the dot product. The dot product produces a scalar. It produces like a number, and it's no longer a vector anymore. The cross product that we're looking at here does produce a new vector. Okay, so common mistake is to like get rid of the I, j, and k. That is not what we need to do in the cross product. We want the I, j, and k because we're trying to create a new vector here. So don't combine all of these, keep them separate. So we're just going to end up with negative 43i. Let's see, this is negative 13, but then we do a minus of that. So that's going to be plus 13j, and then plus just 1k, or just k. And that vector is the cross product of those two, a and b. So let's take a look at some different properties about the cross product, what makes it unique, what makes it what it is. So first thing to note, A cross A. If you were to take a vector and cross it with itself, so like for example, if we did 1, 3, 4 with 1, 3, 4, you would end up here with 3, 4, 3, 4, and you would get 12 minus 12 is 0. You would get here like 1, 4, 1, 4, and you would get 4 minus 4 is 0. 1, 3, 1, 3, you get 3 minus 3 is 0. So any vector crossed with itself produces the 0 vector. So just separate that off there. Any vector crossed with itself produces the 0 vector. Now, the very unique relationship about the cross product and what we're going to be using it for quite frequently in the upcoming sections is the orthogonality that it has, so or perpendicular nature that it has. So the vector A cross B, this new vector we created, so like this one up here, is orthogonal to both A and B. So the vector A cross B is orthogonal to both A and B. It is orthogonal or perpendicular to both of the vectors that went into it. Okay, so again, like this vector negative 43i plus 13j plus k is orthogonal to both of those original vectors that went into it. We can actually prove this. We're just going to prove it for A, but the proof for B is almost exactly the same, just with B's instead of A's in it. So we're going to go ahead and prove it for A. If we want to show that the cross product is orthogonal to A, in order to show that two vectors are orthogonal, we can use something from the previous section, and that said that two vectors that are orthogonal will have a dot product of 0. Okay, two vectors that are orthogonal will have a dot product of 0. So if we take A cross B and we dot it with A, if we can get 0 out of this, then they are orthogonal, and that would suffice as the proof. So get A cross B. So that would be the 3x3 determinant. I'll go ahead and start with the formula in the 2x2s. So that's going to be let's see. So actually, let's go with, we'll start with the formula that we know. So this is going to be A2B3 minus A3B2I minus A1B3 minus A3B1J plus A1B2 minus A2B1 k dotted with the a vector, so that's just going to be a1i plus a2j plus a3k. And now when we dot together, the corresponding pieces multiply. The result will no longer be a vector, so we can drop the I, j, and k once we take the dot product. Again, very important distinction. The cross product produces a new vector, so this is a vector. But once we dot them together, the dot product produces a scalar, so it's not a vector anymore. So we'll multiply the corresponding pieces. So we'll have a2b3 minus a3b2 times a1 minus a1b3 minus a3b1 times a2 plus a1b2 minus a2b1 times a3. And we can go ahead and distribute. So that's a1, a2, b3 minus a1, a3, b2 minus a1, a2, b3 plus a2, a3, b1 plus a1, a3, b2 minus a2, a3, b1. So a lot of writing for these ones, but it does pay off here. So if we take a look at what exactly we have here, a1, a2, b3 minus a1, a2, b3. So those are gone. Negative a1, a3, b2. Positive a1, a3, b2. So those are gone. And a2, a3, b1 minus a2, a3, b1. So those are gone as well. Everything has canceled out, and all we are left with is 0. Right? And again, this is not the 0 vector. This is the number 0. But we are left with a 0. And our goal was to show that A cross B and A are orthogonal. The way we do that is by taking their dot product. If the dot product is 0, then that means they're orthogonal. So this is exactly what we needed to show. So we'll just put a little box there that indicates that our proof is complete. We found what we needed to find. And then I mentioned back at the beginning here, we did this proof for A, but just as a note, it's the same proof for B. So if we were going to prove that A cross B is orthogonal to B, we would do essentially the exact same proof, just with B1, B2, B3 instead of A1, A2, A3. Now, some additional properties for the cross product when it comes to angles between vectors. So we looked at how the dot product relates to the angles between vectors. It's very much related. The cross product is also related, particularly the magnitude of the cross product is related. So if theta is the angle between A and B, then the magnitude of A cross B, or the length of that vector, is equal to the magnitude of A times the magnitude of B times sine of theta. So if you recall the formula from the dot product, it's not too dissimilar from this, except of course we're using sine of theta here. The dot product incorporated cosine. So I want to think about a couple special cases here. What happens when theta is 0 or theta is pi? So if theta is 0, we have sine of 0. And when theta is pi, we have sine of pi. So these are values that we should know from like our unit circle. Sine of 0 is 0. Sine of pi is also 0, which means that if the sine of theta is 0, it doesn't matter what A and B lengths are, right? That tells us that the length of A cross B has to be 0. And there is only one vector that has a length of 0, and that is the 0 vector. So if the angle between two vectors is 0 or pi, so when we say the angle is 0, that means that they are pointed exactly the same direction, or they're parallel. And if it's pi, it means that they're pointed opposite directions, but that's still parallel, right? They're pointed opposite directions, but they're still moving at exactly the same pace with each other. So if the vectors are parallel or pointed exactly the opposite direction, that means that the cross product must be equal to the 0 vector. So, and this is an important property for us, just like the dot product one, right? The dot product of two vectors is 0 if and only if the vectors are perpendicular or orthogonal. The cross product will be the 0 vector if and only if the vectors are parallel. So we can use the cross product to test for parallel vectors. Okay, so the dot product tests for orthogonal vectors. The cross product tests for parallel vectors. There is one important thing to note, because people tend to get this mixed up a little bit. The cross product produces orthogonal vectors. So if we take the example back up here, if you take the cross product of two vectors, the new vector you get is orthogonal to both of the original two. But if the cross product is 0, like we have down here, that is a test that shows that those vectors are parallel. Okay, so if we had gotten something else out of this, if we got 1, 2, 3 out as our vector, this vector would be orthogonal to both A and to B. But because we got out the 0 vector, that tells us that A and B are parallel to each other. Okay, so if you are trying to find a new orthogonal vector, then you take the cross product. If you're trying to test whether vectors are orthogonal, that's the dot product. Okay, so testing orthogonality is dot, testing parallel is the cross product. Okay, so and I know that's a lot of the same words getting just slightly rearranged a little bit. But it takes a little bit of practice. But the cross product is used to show or test that two vectors are parallel to each other. So for this example, it says find a vector perpendicular to the plane that passes through these 3 points. So we know that these 3 points exist in a plane. So somewhere out in space, there's this plane, and there's 3 points on it, P, Q, and R. And we want to find a vector that is perpendicular to the plane. What we can do in this situation, because there's infinitely many points in this plane, we can't just pick a random point and try to draw a vector out of it. What we can do is consider the vectors between these points. So we saw a couple sections ago, you can draw a vector between any 2 points that you want. So I'm going to draw one between P and Q and between P and R. You could also draw one between Q and R, but it's not necessary. By drawing these 2 vectors, and we'll create them here algebraically in just a second, we can then cross them, and the result will be a new perpendicular or orthogonal vector. So it would be orthogonal to both of those, which would then be orthogonal to the entire plane that those points exist in. Okay, so let's write this down here. So we know PQ cross PR is orthogonal to PQ and PR. And the plane they are in. So if we go ahead and get the vectors, so we'll get PQ. So remember how to find a vector between any 2 points. You take terminal minus initial. So we're going to take -2 minus 1, so -3. 5 minus 4 is 1. -1 minus 6 is -7. And then PR. That'll be 1 minus 1 is 0. -1 minus 4 is -5. 1 minus 6 is -5. And then we have PQ cross PR. So let's cross them together. So we'll get I, J, and K. We have -3, 1, -7, 0, -5, -5. And if you want to give this a try on your own, or if you want to like pause the video real quick, see if you can compute the cross product there. So do the formula with the 2x2s and then go through and subtract and do all of that. Then I'll put the answer right here. So the answer we should get is -40i minus 15j plus 15k. So this would be one version of the answer. You could put it, since we did these ones in the bracket form, you could go ahead and put that this way as well. -40, -15, 15. Additionally, the vector that we've drawn, it is very long because it's got components -40, -15, and 15. You could scale it down theoretically if you wanted to. So there's a common factor of 5 in all of these. You can make it -8, -3, 3 as well. You'll see some texts will do that if the numbers are all simplifiable. The reason they do this is because this vector points exactly the same direction as this one. It's just shorter. So it makes the numbers a little bit nicer and easier, but it's not necessary. So all of these are acceptable solutions. So this would be a vector. That's the red vector right here. That is orthogonal to PQ and PR, and thus is orthogonal to everything in this plane. Okay, and we're going to be using this fact in the upcoming sections as well. So to finish us off here, just looking at some quick hits here, some properties of cross and dot products. Some of these we'll use more than others. So remember the dot product, the order didn't matter. You could take A dot B and that's equal to B dot A. That's one of the nice things about the dot product. The cross product does not work that way. The cross product, A cross B is equal to the opposite of B cross A. Okay, or I should say, group this together. Opposite of B cross A. So if you want to switch the order, A cross B is not equal to B cross A, generally speaking. Okay, so if you want to switch the order, you're going to have to negate the B component in order to make them equal. Basically, what ends up happening if you were to flip them, so like if we look at the vector back up here again, instead of drawing this vector, you end up drawing the opposite vector, which is still perpendicular, right? It's still orthogonal, so that's not necessarily wrong. But if you're trying to find like equality, A cross B is not equal to B cross A. It's equal to the opposite of B cross A. If you have a scalar, so like a scalar D, dA cross B is equal to A cross dB. So you can move scalars between the different rows of the determinant. It won't matter. You can even pull it all the way out to the front. It's not going to make a difference. If you take A cross B plus C, that's equal to A cross B plus A cross C. So the cross product is distributive across addition. And it also works forward from the front and from the back. So A cross B plus C and A plus B cross C. We do need to list these two rules separately because, again, moving the order around doesn't guarantee that it's exactly the same thing, right? If the cross product is in front, that could be different than the cross product being back here. Luckily, we can prove that these two are both true. When it comes to A dot B cross C, that is equal to A cross B dot C. So these are getting a little weirder, kind of an interesting relationship here, that you're crossing the back two vectors and dotting with the first, or crossing the front two vectors and dotting with the last, and they will be equal. They'll be equivalent. And then the last one, we're not going to encounter this one too much. It goes into kind of a different direction than we're going to be heading. But A cross B cross C is equal to A dot C times B minus A dot B times C. So just a very interesting relationship to see how crosses and dots all interact with each other in very unexpected ways. But again, that last one, we're not really going to be encountering that one too much. But some of these earlier ones we definitely will encounter in our journeys with cross products. But that brings us to the end of section 12.4, and that is our introduction into the topic of the cross product.